Yay, we get to talk about money. So interest compounded on a principal investment. So principal investment just meaning like your initial amount. It's your principal. Measured in dollars at the end of each year. What? Let's read that again. Interest is compounded on a principal investment at the end of each year. Okay, so the interest comes at the end of each year from your starting amount. Got it. Man, English sometimes, eh? So if the total amount of the investment after n years is an amount A, is equal to your principal amount times this, like this rate factor, so 1 plus the rate over 100, all to the power of n. Yeah. So this bit in here, so if our rate as a percentage was, let's say, 3.85%, that would be 1 plus 3.85 over 100, which is 1.0385. No, too many O's. 1.0385. And so when we multiply our initial amount by that, it's saying it increases by 3.85% each year. Right? And then the next year we'd times that amount by the rate, and it compounds. It compounds annually each year. Alright, so Anushka has way too much money, $20,000. So that's their principal amount. And the interest rate is 3.85%. Right, so how many years will it take for her investment to be worth $25,000? So this is the amount that we want to get, $25,000. We know her principal amount is $20,000. And we know the rate is 3.85%, which we could plug in there. Or in this case, they were quite generous, and they gave it to us there as well. So 1.0385 all to the power of n. And so the question is asking how many years. So we're looking for that number n, number of years. So to do this, we could divide both sides by 20,000. So 25,000 divided by 20,000, which is the same as 25 divided by 20, 1.25, equals 1.0385 to the power of n. All right, now looking at this, we have the unknown in an exponent. So to bring it down, we can use logarithms. So remember, logarithms are the inverse function to exponents. So if we take the log of both sides, like so, still use the brackets there, we can now use a log law, which brings the power out to the front of the log, right, to multiply by it. So log 1.25 equals n, so that's the power of log 1.0385. And so now n, which is the unknown, is no longer in a power, right, as the index. We can now solve for it. So we'll divide both sides by log 1.0385. So log 1.25 divided by log 1.0385 will equal n, which is just a number. So on our calculator, we can type log, which is just near alpha, towards the right and down one. So log of 1.25 divided by log of 1.0385. Execute, which is 5.9. Now let's think the question. So that's 5.9 years. Does that make sense? In this case, no, because the interest is compounded at the end of the year. Right? So we need to round up to 6 years. If, however, it was compounded every minute, then having a decimal like 5.9 would make more sense. All right, so that's not too bad. 6 years to get $5,000 from a $20,000 investment, but this interest rate is quite low. So, Semesi invests his money at a different interest rate. Okay, let's hope it's higher. His investment will double in value after 12 years. What is this? What is the interest rate for this investment? Okay, so the unknown here is the interest rate, or R. We're given that his investment will double. We're not given what his initial amount was, though. Okay. So let's try put this information into an equation. So just a reminder, this equation up here relates the investment amount to the initial amount, the rate, and the number of years. So let's use that. So P 1 plus R over 100 to the power of n. My R's and N's look quite similar. All right, so we could say, let's let his principal amount be, I don't know, A0 for like initial amount. We could use P, but I'm answering this question. I can do what I want. So A0, naught meaning initial. And now it will double after 12 years. So when n is 12, his amount, right, A, will be double his initial amount. So it will be twice as much as his initial amount. So here we've set up the problem. I've introduced this variable A0 just to be Semesi's initial amount. And we know when n is 12, so after 12 years, the total amount will be twice the initial amount. So what I can do now is, instead of P, I can put A0. Instead of A, I can put 2 times A0. And we'll see the magic that happens after. So instead of A, we have 2 times A0. Instead of P, we have A0. Instead of 1, we still have 1. The rate is what we're looking for. And of course, this happens when n is equal to 12. All right, do you see what's going to happen now? We can divide both sides by A0, which effectively cancels out that unknown. So we don't actually need to know how much Semesi invested initially. We just needed to know that after 12 years, it will double. So we're left with 2 equals 1 plus R over 100 to the power of 12. Now we can take the 12th root of both sides, because the 12th root of something to the power of 12 is the something, in this case 1 plus R over 100. 12th root of 2, that's just a number. We can now subtract 1 from both sides. And finally, we can times both sides by 100. And if we plug that in on our calculator, like so, 100 times 12, shift hat is the, so the little x root means 12th root of 2, minus 1, bracket. gives us 5.95 approximately %. That's a much better interest rate, right? Almost double, not quite double. But yeah, so Samisis picked a better investment, and we worked out his interest rate by introducing this variable A0, substituting it into the investment amount equation. We're able to eliminate A0 and then solved for the rate.